was kind of in that. I showed up at 9:35.
That's unfortunate.
Yeah.
Okay, I'm going to get started here. What I first wanted to cover, I said I would yesterday, was that for this first week, Linux Lab 1 is just a reading. Please make sure you do it. And I think it was, a quote, probably incorrectly, was a Genghis Khan. If you have a week to fight a battle, you research for 6.5 days and fight the battle on the latter part of that 7th day. So reading, the background reading is critical to your understanding. If you properly research and read for Linux Labs, you'll have absolutely no problems whatsoever. When students have challenges, difficulties, it's because they didn't do the reading, okay? Now, there's, of course, exceptions to the rule, and of course, again, I will get you over that. But please make sure you do the reading. So Linux Lab 1 is right in this menu off CISS100.com, Linux Lab 1, Ubuntu Linux Introduction. And please read that entire page, too. One of the things that we're striving for in computer science education, actually education in general across the country, is security. And that's going to become even more critical. We look at robotics, sensors, Internet of Things, everything that's going on, security. And you cannot understand security unless you understand foundational computer science, computing. And really, it boils down to the operating system, because we're going to learn the operating system is the resource manager. It's coming in a few weeks. But the more operating system knowledge we have, the better we can secure our computers. Okay, and that's what we need to do. So today we're going to begin with the textbook, Understanding Computers, Chapter 1. And I do run off, down at the bottom of this lecture module's menu system is textbook PowerPoints. So these are there for you if you'd like to reference them. I do use PowerPoints because they will minimize the amount that I digress. They'll kind of keep me on track. So I kind of apologize for using them. With respect to the presentations from the chapters, a lot of the content, especially if the textbook presents it very well, I'll just gloss over it or not even present it as well. If the textbook presents it well, it's kind of understand intrinsic computing knowledge, I'll pass over. And I will add content to the chapter material. Note, though, that you are responsible for the textbook content. Okay, I'm going to give you a lot of extra information, and if I do require it, I'll tell you that I require that knowledge. But for the most part, you are just responsible for the textbook. Kind of create a nice foundation there. Okay, so here we go. Now, also as an introduction, computer science. When we're learning computer science, we tend to get a kind of a broad perspective, and then over time we narrow it down. We get more and more detailed, more and more precise. And we find that even within this textbook. The first chapter is kind of this big, broad, surface level overview. And then in subsequent chapters, we'll get into more and more detail. So that's a lot of what this first chapter is. So the beginnings. What is a computer? Programmable electronic device. Accepts data, performs operations, stores the data, okay? There's a model here of the basic operations, input, processing, output. Now, this author also adds storage and communications. Not every author will add those. The real basic model is just input, processing, and output. And this applies to all different scales of computing. Down the road, we're actually going to look at the CPU, the central processing unit, okay? That's actually sits on the motherboard. And what does it do? It takes input, it does processing, and performs output. Another example on a more granular scale, this computer here. Okay, I can type something in at the keyboard, input. The computer itself as a whole does processing, although it's still the CPU, and then provides me with output on the screen. Okay, so I have input, processing, output taking place at the CPU level. I have it taking place at the computer level. It also takes place on the information systems level. And I can, as an example, look at your scheduling. Okay, the college has an information system to manage scheduling. Some of you may have used Wired to add your classes. So what is that input? Well, you input your AVM, your username, password inputs, okay? You input the schedule that you want, and the outputs of the information system are your schedule, your financial aid calculation, okay? Things of this nature. So again, we have this input processing output process occurring at many different scales, very discrete or finely granular at the CPU, a little larger at the computer level, and also fully blown at the information systems level. So memorize this, input, processing, output. And now again, the author will add storage and communications. And we'll just kind of accept that face value. Okay, so I said yesterday, from this point forward, we are all information scientists, okay, information systems professionals. Okay, so we need to understand what do we actually do in computer science. We need to understand the distinction between data and information processing. Okay, so data, raw, unorganized facts, text, graphics, audio. Information, it is data that has been processed into a meaningful form. And of course, information processing is converting the data into information. So let me jump ahead. I'm actually going to give an example first here. Take a look at this, data. 012569856. Does this mean anything to anyone? Okay, raw, unorganized data. It's kind of meaningless, okay? But what if I organize it? What if I put it into a table and give the heading SSN? Does this suddenly make sense? Okay, just what I did there was information processing. I took data and turned it into information. I'm going to jump back here and take a look at the information hierarchy. Okay, so as information scientists, information systems professionals, we always strive to push the data as high up this pyramid as we can. So what do we see? We see data, information, knowledge, and wisdom. And in my last example, simply by taking those numbers and putting it into a table with the heading, the column heading, SSN, I conveyed information. I took it from data and turned it into information. Now take a look at that next one, knowledge. Okay? So what if, well, what do we know, right? We took the data and pushed it up the hierarchy to information, but we know more about that social security number, don't we? It's intrinsic to us. We have context. We know that a social security number is unique text, right? It corresponds one-to-one with an individual. That's actually a mathematical mapping. That's a relationship. For every social security number, there is exactly one person, right? And hopefully it goes the other way around, the other way as well, okay? So this corresponds to knowledge. So if we can actually encode that, okay, what a social security number is, it's unique text, corresponds one-to-one with an individual, we can actually push that data all the way up to the knowledge level. And why is that beneficial? Interoperability, integration. Because nearly every country, I'm probably going to say every country, has something similar to a social security number. And I learned a year ago or so that the Chinese, they use actually an 18-digit and character social security number as an equivalent. Because if I can encode that, SSN is unique text, corresponds one-to-one, I can translate it. I can create up an equivalent within China, within whatever other country or whatever other system. So if I can push data up to that knowledge level, my ability to communicate and interoperate and integrate becomes more important. Now that fourth level was wisdom. How do we do that? Well, again, in computing today, artificial intelligence, and we're going to talk about AI a lot, okay? Because there are advocates and detractors, and in many areas we should be questioning not only if we can do it, should we be doing it? Okay, but we'll look at that down the road. Now, something else here I want everyone to become aware of. SSN is unique text. I have it there as text, not a number. Why? Okay, we get to this down the road. Within a computer, we're actually dealing with symbolic representation, right? If I want to assess traffic, I of course can't put cars and trucks and roads into the computer. What do I need to do? I need to create symbolic representations. And that's what we're doing for data, for numbers, for everything. SSN, I'm encoding, symbolizing as unique text. Why? Look at that social security number. There's a leading 0. What happens to that leading 0 if I encode it as a number? It's gone. It's gone. Is that 0 significant? Yes. Okay. So this is something as information scientists we need to remain aware of. And again, I understand no one here has ever been presented with this. This is entirely new to us. And that's one thing I failed to mention yesterday. In this program, CISS program, we don't presume any incoming knowledge about computer science. We start at the ground level, okay? So some of you who have significant IT skills already, you may think that this is basic, and it is. But we have to start with a proper foundation, because if you miss just even one piece, okay, it's going to negatively affect what we learn down the road. Okay, so computer science, computing, computers. We nearly always start with a review of where we've come from, understanding our history. So, and that's what every computer science text will begin with. So we take a look at the evolution of computing, okay? Fairly recent invention. If you think about it, the biological sciences, mathematics, physics, chemistry, all of these things have been around and studied for hundreds of years, even thousands of years in some cases, okay? When you look at computing, really 1940s, we're in our infancy in understanding computer science. And that presents challenges, and I'll illuminate these as we go. So, pre-computers, early computers, I won't read that. One thing that is omitted here, though, is the loom, okay? The weaving loom, okay? This was actually programmed back in the Industrial Revolution in the 1800s to create patterns and things like that in fabric. So it's kind of an omission here, but that was an early type of computer because it was programmed. I want this string pattern in this cloth. So, okay. So we talk about generations of computers. First generation, powered by vacuum tubes. The critical thing here is that to change programs, to change what you're processing, you'd actually have to rewire the computer. By the way, any musicians here? Anybody still using tubes? Way to go. But if we look at this in a little more detail, by the way, when I talk about generations of computers, I'm talking about generations of hardware at this juncture. There are equivalent generations in operating systems, equivalent generations in programming languages, and they kind of moved or advanced in lockstep fashion. So when we look at first generation to second generation in hardware, there was also an equivalent or complementary advance in operating systems, a complementary advance in programming as well. Okay, so first generations of computers use tubes, second generation use transistors. And I said in the first generation, to do something different on a computer, you actually had to rewire it, okay? Second generation, we now have basic input and output because we have punch cards and magnetic tape. So at least I could give the computer different data sets. I'm running the same program, but now I can feed it punch cards so I can send in or provide it with different types of input, get different output, things like that. Okay, so second generation was transistors. Third generation, we saw the evolution to integrated circuits. And take a look as well, keyboards and monitors. Now with keyboards and monitors, we now have interactive input. In that second generation with punch cards, you fed it the punch cards and the program either ran to completion or crashed. And that's it, okay? No interaction. Now with the third generation, we now have keyboards and monitors. So again, we're seeing the evolution of the operating system to what it has become today, of course, with the graphical user interfaces that we're accustomed to. Fourth generation, microprocessors. Okay, so microprocessors, of course, are in all our PCs. They're in our phones. They're in our tablets. We're seeing them in devices, robotics. We're seeing a lot of new devices. The Arduino or the Raspberry Pi. I don't know if anybody's seen this, but they're being used a lot for really low-cost robotics creation, innovation. We see the evolution of input-output, keyboards, mice, monitors, printers, etc. Flash memory, disks, okay, networks. Fifth generation is speculative, okay? There's no precise classification. Some people will say it's one thing, others will say it's another, okay? We don't actually know what it is. We'll likely use voice and touch input. Well, there's also, people are controlling computing now with thought-based computing. There's gesture-based computing. We're all seeing, the games that are monitoring our gestures, body language, facial expressions, things of this nature. There's a car now that actually monitors your facial expression. Okay, so if you see shock and horror, it's going to apply the brakes. So all these things are coming. Hardware. Okay, just like with many of the other sciences, we perform classification to understand a discipline. So when I look at hardware, I can further classify it as internal hardware or external hardware. Internal, of course, is located inside the main system unit. External is outside. And again, the lines here are becoming more and more blurred. Because you look at an iPad, the thing is entirely contained. Should something go wrong, in many cases, it's replace the iPad, replace the phone, okay? And recall what I said yesterday. We're not just looking at technology. We're looking at that business, IT, society triangle, okay? We have to be aware of the effects. And one of the effects of these all-in-one systems, the phone, the iPad, when they go bad, we're throwing them out. Where are they going? Okay? Landfill. It is not an environmentally sound approach. And we really need to be aware of this. Okay? We need to think about it going forward. And there's several solutions I'm going to provide you with. This also is a moving target, internal hardware and external hardware. Back when I was in grad school, and I was working on silicon graphics machines, almost everything was external. So the hard drive sat on your desk, or 2 or 3, your CD drive, everything was external. The only thing really in the box was, the CPU, the motherboard, and then connections to peripherals. And this created a terribly messy desk, okay? Wires everywhere. But should one component fail, it was real easy to just replace that component. It's a much more green approach. Okay, so we have to look at that. And again, today's consumer just wants convenience, all in one. Today's consumers have forgotten how to look under the box. Okay, and hopefully we'll move far, and we will move quickly and far beyond that. If you think about it, when something goes wrong on someone's computers today, what do? The first thing, hello, tech support. They're calling for help. People don't even try to help themselves, do any investigation on their own. So, and there are problems there. They're very secure, problems of security there as well. Okay. Input devices, processing, output. We have a whole chapter on input, output, so I'm not going to say much about it right now, because we're going to talk about it for an entire week. Again, as soon as a textbook is published, it's out of date. So, and that's the case for the 14th edition, and it's no fault of its own. So I added some things here. For input devices, sensors. Sensors, we're about to witness the emergence and quick evolution of the Internet of Things, where our environment is just going to become sensor-rich. There are just going to be sensors everywhere. Robotics, same thing. Okay? And there are good things and bad things about this. Okay? A positive thing is sensors can reveal dark data. Okay, so there's a new term for you, and I won't require it at this point. Dark data is previously undiscovered data. As you turn around, it's specifically important for marketing. Okay, Best Buy installed cameras at the front of their store, and they observed that 95% of the people, when they walk in Best Buy, turned and looked right. So they moved higher price and associated equipment to the right, and their sales went up. So it's the application of IT right there for marketing benefits. Okay. Down below, output devices. Well, I have sensors there too. I also have haptics. Haptics are vibration. And you're seeing these, of course, automobiles when you're reverse, okay, with the cameras now. Collision detection. Well, okay, it's nice that they play a sound, stop your radio or whatever, but a company found that if your seat starts to vibrate when you're about to have a back into something, it gets someone's attention just like that. Okay, so all these new types of input-output devices are becoming prevalent. Do you on your phone? That's right.
That's what they call the vibration. The haptic.
Nice. Yeah, and I mean we have them on our phones too for text. Rather than you can turn the volume off and it vibrates. So, storage devices. This too is a moving target. And recall what I presented yesterday, where storage is seeing similar increases in storage capacity as Moore's Law. Every 18 months it's doubling, price is just dropping. But we're also seeing, and we have a whole chapter on storage, so I'm not going to dwell on it too long here, the increased use of cloud storage, G Drive, Apple's, okay, everyone, Box.net, Dropbox. How many people are using a cloud storage device? A few? There are concerns about it, right? Of course, you're putting your information up in the cloud, and why? Well, there's a business model there. So the company sees an advantage to having you store your stuff on their servers because they can look at it, right? And nothing comes for free, okay? That's pure marketing analysis. Okay, software. Again, we can further distinguish or classify software as system software or application software. The most obvious instance of system software is the operating system. And operating systems knowledge is probably some of the best knowledge that you can have. Okay? Security starts and ends with the operating system. It is the resource manager. And I'm going to talk about that at length. Please, there's a link there, and I actually have it in the notes. Please, if you will, tonight or before next week, read about the boot process. It's important to understand how a system, how a computer boots up. And in a nutshell, what happens? I turn the computer on. A series of clock cycles takes place, and then it does a power on self-test, power on self-test. And it tests its memory, it tests peripherals, the mouse, the keyboard, whatever is attached. So it kind of takes an inventory. And along with the inventory, it says, are you working? These instructions, by the way, are located in the read-only memory, ROM. Okay? And at this point forward, we're going to need to distinguish between memory and storage. Okay? And again, recall what I said yesterday, to the uninitiated, to the unaware, someone reading computer science just blows right through storage. Oh yeah, I know what storage is. Storage is stable, it's non-volatile, like your hard drive. Memory is volatile. You turn the computer off, it goes away, and everybody has experienced that. You're working on Microsoft Word, document, whatever, you lose power, your computer crashes, your latest changes are gone, okay? So understand the distinction between memory and storage. So returning to the boot process, I turn the computer on, it does a power on self-test, post. Those instructions are located in its read-only memory. And actually further qualifying that, it's electronically erasable, programmable read-only memory, so EEPROM. And then the computer jumps to the storage device, to the master boot record, and loads the operating system. So here's my question for you. Some of you have probably heard of a boot sector virus. Why is a boot sector virus so bad in light of the boot process? Okay, so that's for Tuesday. Please try to determine why it's so bad. Try to figure that out. Okay, so when I look at operating systems, there are three major operating systems: Windows, Mac, and Linux. Linux, by the way, is the basis of Android, just so you know. And Mac is actually converging. Their iOS and their operating system, they're both using the Swift programming language now. And we're seeing that too. Windows is trying to follow suit to create a converged operating system for both its desktops and its mobile platforms. And we'll look at why that should happen. Application software performs specific tasks. Microsoft Word, Microsoft Excel, photograph editing, music composition, things of this nature. I'm not going to say much, or if anything, about computer users and professionals at this juncture. We're going to look at this throughout this course. We'll understand it better when we learn about programming, when we learn about systems analysis, when we learn about database management systems. So we'll understand more about what these, specialized professionals will do, and hopefully it'll give you some guidance into what you want to go into as well. Okay, again, just continuing on, this is a broad overview of computing, kind of a classification. If we look at embedded, mobile, personal, the biggest growth in the near future, well, of course, mobile devices, and we're seeing Apple Watches and things like that now, is embedded computing. And embedded computing includes robotics, which is going to be huge, okay? Embedded in sensors, okay? So, we've already seen it in refrigerators and things of this nature. It's going to become even more pervasive. There's something out there, and I'm not sure if anyone's aware of it, and we'll take a look at it. It's called Li-Fi, L-I-F-I. And it's using, well, we know about Wi-Fi, right? Wi-Fi uses the electromagnetic spectrum, radio frequencies. Li-Fi uses lights, LEDs. And that has the possibility of completely changing our networking, completely changing the way we use intelligent devices, okay? You're no longer asking Siri on your phone, you're asking Siri on your light, okay? And it brings a smile to my face, but in a fearful way too, okay? Because that will allow is just eavesdropping, surveillance, all kinds of things. And we're there now. We're looking at Li-Fi within the next couple of years, and the general public is not aware of it. So we'll look at that as well. Yeah, so all these, Aldous Huxley's Brave New World, 1984, all these science fiction novels from the past are actually realizable. So the smile on my face is actually fear, so just so you know. Okay, thin client. Thin client was around back in the 60s. Okay, essentially a thin client it's a dumb terminal that gets its information from the server. So this is the classic client server process. Pizza from the deli and brew. I walk up, there's a server there, can I have a slice? The server, they hand me the slice, they hand me the resource. Same thing is taking place with thin client, okay? The client gets its resource from the server. Now in computing, what kind of resources do we have? Well, we have files. We actually have programs, okay, or processes, more correctly put forth. If we look at what's going on in the ACE is the Academic Computing Environment, ACE, on this campus, okay? And we're running a virtual desktop interface, VDI. And again, I apologize for all these acronyms, but you'll get used to it. So when you're in one of the labs and you're using Microsoft Word isn't really running local on your machine. Its components are, but largely it's running back on the servers. You're being supplied Microsoft Word from the server. So it's actually just giving you a web interface. The user doesn't see the difference. There are benefits to this, okay? Because of course, if your local machine crashes, server's running on generators if necessary. It's not going to have, be susceptible to a power failure. Okay, so that's good. Servers are backed up because very few people back up their work, despite, how many times we tell them, back up your work, they don't. So when their computer crashes, oh, my paper's gone. Where if it's on the server, it's backed up. Okay, so there are many advantages. There's ubiquitous computing. So I can walk from station to station and my work follows me because it's coming from a server. So we'll look at the advantages of that, okay, down the road. So internet appliances. Here, again, the distinction is becoming blurred because, again, we're moving towards the Internet of Things. We're moving towards increased use of sensors. So this description or definition of internet appliance is changing. Computer network, I'm not going to say much about. We have a network that connects computers together. Okay. What you need to know at this point, you need to be able to distinguish between the internet and the World Wide Web. The internet is the, well, I can read it, of course, largest well-known computer network. It's the infrastructure. Okay. Much like our highway system out there. Our highway system is the infrastructure. It's the roads we drive on. Okay. But it's not just the highways themselves, right? They're rules. Stoplights, yield, stop signs, rules of right-of-way. Okay. So the internet, while it is the physical infrastructure, the fiber optic cables, the coaxial, the copper cables, it also has rules that govern transmission. So it's two things there. The World Wide Web is just one thing that runs on top of the internet. Many things use the internet. World Wide Web is just one of them. And we'll look at this in an entire chapter. We'll spend an entire chapter on this. World Wide Web depends or uses the Hypertext Transfer Protocol, HTTP. And you've probably seen this. If I look at my browser bar, I'm not seeing it there, okay? I'm just seeing worldwideweb.cis@100.com. But for many sites, you'll see the HTTP or HTTPS, which means it's the secure Hypertext Transfer Protocol. Okay, so I'm not going to say much about this now because we have entire chapters each on the World Wide Web and internet. I don't want to overburden anyone at this point. Okay, so to access a network, we need a modem or network adapter. Okay, network adapters typically refer to them as network interface cards, NICs. So of course your phone has one. It actually has two. To connect to the cellular network and to connect to the Wi-Fi network, probably, and actually Bluetooth too. Your computer probably has an internal one or at least a card because it probably has an Ethernet port. Okay, so that's the network adapter there. In the home, of course, if you're using Time Warner or if you're using Verizon's DSL, you have a modem, okay, a modulator, demodulator, because I need to go from digital to analog and back and forth. Okay, again, all of these concepts, items, we're going to look at in greater detail in subsequent chapters, so I won't dwell on it. Okay. Should know what an IP address is. Okay, it's text-based, but it looks numeric. Okay, 192.168.32.1. Okay, something like that. And we will explore. We'll actually go into the computer settings, so you'll be able to look at this and troubleshoot it. So we will do this as well. Uniform resource locators, URLs, are for humans. We don't remember numbers well. If I had to remember the IP address of, I'd probably remember two. I'd remember ESPN.com and Hudson Valley, and that would be it. Whereas with a URL, all I need to remember is ESPN.com. okay? hvcc.edu, okay? Much more user-friendly, much more accessible. I'm not going to say anything about email addresses, okay? Domain names are top-level domains, okay? Well, actually, domain names have a top-level domain, okay? So .edu, .gov, .com, something like this. And I won't say much more about that. Okay. URLs do uniquely define a web page, and the protocol are standard. And implicit in this, again, it's www.cis, so it's World Wide Web. Implicit here would be the HTTP. I could type that in there, and it would bring me to the exact same location. HTTP : / tells my browser that I'm looking for a hypertext transfer protocol, or I'm using the hypertext transfer protocol. And I'm not going to say much about email addresses. Searching the web. We're first of all, we're moving towards the semantic web, okay? And the move to the semantic web, the third generation, so to speak, will be transparent. Users won't even, know it's taken place. But many people still don't know how to search the web. Why? Because they don't understand the architectural framework. Okay? Can anyone give me a topic you'd like to research? Someone, give me something. Anything. Come on.
Odds of the games this weekend.
Odds of games. Okay. How would you compose that search?
Go search.
No, what words? As an example.
Vegas odds of Broncos Patriots.
Okay. Would you use the keyword of? And let me back up. The web today is stored in a database. Okay, I'll use the example. When I go to ESPN.com, they don't have a static page ready to deliver to me. Okay? What actually happens is when I type in ESPN.com, of course, and there are many things that occur before this, so I'll just kind of gloss over it. It hits their web server, and it sees a request for their ESPN.com, which would be their home page. But that page doesn't exist. So it hits their Apache web server, goes down to the PHP, which is the processing level, which says, pull out all of these aspects from the database. The video, the articles, all of these things are sitting in a database. They're passed up from the database to this processing level, and then finally, they're sent out back to me as a complete web page. So when I search, I'm actually searching a database. And if you're thinking about what's going in a database, I'm not using the words of, okay? NFL, odds, maybe Las Vegas, okay? All of these things. I can give an example, and I think it's from the textbook. People say they're searching for the running speed of a cheetah. What is the running speed of a cheetah? Well, think about it. Where is it getting this information? From some academic article, right? And is that academician writing, what is the running speed of a cheetah, and then answering their own question? No, they're writing cheetah's top running speed. Those are the keywords. So when you're thinking about search, you actually have to search, we know this, from the academic perspective. How is the information being recorded? As in, who's writing the paper? If I was writing this paper, how would I phrase it? Now, marketing actually has to do the other thing. They actually have to go out and think about how is someone, because I want someone to find me, okay, if I'm a marketer. How do I write this so that I show up in people's searches, search engine optimization, okay? And we're going to look at that interplay throughout this course as well. Because again, most people are not aware of it. So we'll look at that. Okay, email, not going to say much about. Computers and society. we are going to look at this in depth. Again, everything we look at with IT, we're going to look at on its impact or effect on business and its effect on society. Okay. The second bullet there, second line, earlier medical diagnoses, more effective treatment. Do you know who's in the medicine health game now? Google. Why? Because they're crunching data. And what is medicine? Evidence-based. And Google is in a prime position to look at that. You know, here, all these symptoms or outcomes or diseases, what's the commonality? It's pure data analysis. I don't know if you know this. There's a group of 20 computer science PhDs, and they formed kind of a think tank, and they applied this machine learning algorithm. And they were able to come up with, over a 1 or 2 month period, I forget what it is, more new usable drugs than several pharmaceutical companies. And these PhDs in computer science had no medical training. How did they do it? Pure data analysis. That's it. And machine learning. So things are shifting. Things are shifting for good or for better or for worse to come for where everything is just going to be reliant on computer science. And again, with artificial intelligence, I hope it's for the better. Okay. Computer-oriented society, risks, stress, health concerns, yes. MIT did a study that people who use Facebook actually feel worse about themselves, you know, on and on and on. And I won't go into this. We'll look at this down the road. We'll look at viruses and malware and security. We'll look at spam, increasingly used to thwart security, privacy issues, and things of this nature. And some of it is, well, to me, downright fascinating. Differences in online communication. There are huge differences. University of Oxford, England, did a study contrasting email with traditional letters. And for some reason, people take offense to email more than letters. They send the same letter to someone's email address, and of course they're sending it to someone else, but they're doing massive A/B analysis. And for some reason, the same letter, when it arrives via email, people object to. They take offense to it. There's something personal about it. Whereas, and I say it's a letter from a creditor. Whereas you get it in the mail, oh, fine, I open it, I rip it and throw it. But when it comes via email, I feel violated, or they found that people felt violated. There is a difference. And we can see that, you know, Twitter, Facebook, all these other things. There's just something different about online communications, and we need to be aware of it, okay? We need to be aware of it for teaching, for training, for all these things. Marketers especially need to be aware of this. Okay. Okay, I won't read that. Later on, we actually have a blog bill of rights or so I'm going to show you about what to do online, how to choose and use words carefully, because different words, which mean the same thing, will be construed very differently. They just have a very different tone about them. We'll take a look at that as well. We know about the anonymity factor. Yeah, it's there. Information integrity. We're going to look at how do we evaluate sources. So we will look at that as well. And that is it. So again, let's see if I can scroll up. Where is it? Again, you should have read chapter 1 for today. And I realize it's kind of a steep learning curve to get going here, reading one chapter the first night and then reading Linux Lab. If possible, well, please read Linux Lab 1, this reading material this weekend. Please try to read chapter 2 before Tuesday's class. And then we're right on track, okay? Then you get into the habit of reading the text before the presentation, and we'll be set. That's it. Anyone has any questions or concerns, please keep me in the loop. Have a great weekend. See you Tuesday.